Hello, we are Group 11. This is our video presentation for Lab 1 in Stafræn rafeindatækni. In practical exercise 1, the purpose was to try out different integrated circuits to get to know different types of logic gates. For part 1, we connected 5 different ICs to the following circuit, and we filled out a truth table for each of them. From the truth tables, we could see which type of logic gates we were examining. We started with the 7400, and after filling out the truth table, it was clear that it was a NAND gate, because a NAND gate only produces a false output when all its inputs are true, which is opposite of a AND gate. The next IC we examined was the 747266. After filling out the truth table, we could see it was an XNOR gate, which only gives a true output when both inputs are either true or both false. The next IC is the 7408. We filled out a truth table again and we saw it was an AND gate. An AND gate only produces a true output when both its inputs are true. The next IC is the 7432. We filled out the truth table. When we looked at it, we could see it was an OR gate. An OR gate produces a true output when either one of the inputs is true. The next IC is the 7486. From the truth table, it is clear it is an XOR gate. An XOR gate outputs a true statement only when either input is true but not both. For part 2, we used the same parts in the circuit, except we used the 7402 and 7404. Since their pin configuration are slightly different, we had to make some minor adjustments for the connections. We started with the 7404. From the truth table, it was clear that it was a NOT gate. A NOT gate produces a true output when its input is false and vice versa. Next up was the 7402, and from the truth table, it was clear it was a NOR gate. A NOR gate is the opposite of an OR gate, so it only produces a true output when both its inputs are false. In part 3, the purpose was to use an IC to connect logic gates in different ways to produce function of other logic gates. First up was the 7402, which has 4 NOR gates within. We combined the 2 inputs of the NOR gate to one push button. The result is a NOT gate. Then we connected the output of a NOR gate to both inputs of another NOR gate, and the result is an OR gate, which makes sense because the NOT gate flips the results of the NOR gate. Then we connected the outputs of 2 NOT gates to the input of a NOR gate, and the result is an AND gate, which makes sense because when both the inputs of a NOT gate are true, the inputs of the NOR gates will both be false and the output will be true. Next up was the 7400, which has 4 NAND gates within. First we connected both the inputs to one push button, and the result is a NOT gate. Then we connected the output of a NAND gate to both inputs of another NAND gate. The result is a AND gate, which makes sense because when you connect a NAND gate to a NOT gate, the NOT gate flips the result of the NAND gate and therefore making an AND gate. Then we connected the outputs of 2 NOT gates to the input of a NAND gate. The result is an OR gate, which makes sense because if the outputs of the NOT gate are both true, the result from the NAND gate is false, but if either outputs of the NOT gate is false, the result is true. Practical exercise 2. The purpose of part 1 was to build an half adder and half subtractor and examine how they work. First up was the half adder. After building the circuit and filling out the truth table, it was evident that we had an half adder. When both push buttons were 0, the sum and carry are both 0 as well. It isn't until both inputs are 1 that the carry will be 1 and the sum 0, which fits to the adding rules of binary numbers. Next up is the half subtractor. The truth table gave us a clear picture of how it works, and the result fits the rules of subtraction of binary numbers. When push button 1 and push button 2 are both 0, the difference and borrow are both 0. When push button 1 is 0 and push button 2 is 1, we have a difference of 1 and borrow of 1. And when you have push button 1 is 1 and push button 2 is 0, we have 1. And when push button 1 is 1 and push button 2 is 1, we have a difference 0 and borrow 0. In part 2, we built and examined the SR latch. The truth table gave us results that fits the function of an SR latch. When we first connected the circuit, Q complemented was high, but bear in mind that it is unpredictable which one will start off high. And when we pressed reset, nothing changed. When we pressed set, Q turns high, but when we press both set and reset, it is unpredictable which one will be turned on. In the last part of the exercise, we looked at a JK flip-flop, which is a more complex flip-flop than the SR latch. The difference between them is that the JK flip-flop does not have the problem of the illegal state of the SR latch. When we connected J to VCC and K to ground, we have the set state. When the button is pushed, Q complemented, which is the bottom diode, it stays on. Next we set J to ground and K to VCC, and we have the reset state. When the button is pushed, Q complemented turns off, and Q, the fourth diode, turns on. And when the button is pushed again, it stays the same. Next we set J and K to VCC, and we have the toggle state. When we press the button, it switches back and forth between Q and Q complemented. Next we set J and K to ground, and then we have the hold state. When the button is pressed, nothing changes.